Hello once again. So now we're back to finish up our discussion on rational functions. And so in this second part of the video, we're going to look at some example problems of graphing rational functions and go through a basic process for graphing rational functions. Now, before we do that, what I wanted to do, there was one more aspect of rational functions that I needed to cover, and this deals with the holes in the graph of a rational function. Now, this is something that can occur when there's a common factor between the numerator and the denominator of a rational function. And these are things that you want to identify before you go through the process of trying to sketch a graph of a rational function. So an example that we have here is the function f of x equals 3x minus 6 over x squared minus 4. Now, if we examine this particular function, we will see that once we factor everything out, we will then see that there's a common factor between the numerator and the denominator. In the numerator, if we factor that out, we have a common factor of 3. So that gives us 3 times x minus 2. And in the denominator, you have the difference of two squares, which is x minus 2 times x plus 2 times x minus 2. And so both of these have a common factor of x minus 2 that we can cancel out. Which will give us the equivalent expression of 3 over x plus 2. Now, when we take a look at this, what we're saying here is that the function itself is mathematically equivalent to 3 over x plus 2. However, one thing that has to be considered is that since the original function had the denominator of x squared minus 4, this function will have a domain. The domain here will be all real numbers except plus or minus 2. So even though the expression is equivalent to 3 over x plus 2, which by itself would only have a domain of all real numbers except for negative 2, since the original function had both x plus 2 and x minus 2 as factors, the domain is always going to be based on the original function, not necessarily what the simplified version is going to be. So then if we look at the graph of this function, we'll actually see that play out. All right, so here we have the graph of the function. And notice here how we do indeed have the vertical asymptote at negative 2, which is indicative to our equivalent statement of it being 3 over x plus 2. But then note here at positive 2, what we have is a hole in the graph. Okay, and that hole corresponds to where we had that common factor of x minus 2 when it canceled out. So when there are common factors, the graph will not manifest as an asymptote, but it will manifest as a hole. And that's why you want to identify those before we begin the process of graphing the equations or the rational functions. So that's the thing you look for. So what's to look for? You look for the common factors between numerators and denominators. And it's a good idea to factor everything out in the numerator and the denominator of a rational function before you get started. And if you do that, you'll very easily be able to locate the holes in the graph. So now let's go ahead and take a look at the process for graphing rational functions. Put this down on the next page. All right, so here are the basic steps. First thing you want to do, and I call it step 0 because not all rational functions will have holes in the graph. It's something that you just want to check before you get started. So first thing, identify any holes that you have in the graph. And all you have to do there is just factor it out and simplify, canceling out any common factors. The common factors will be where the holes are located. Then step 1 is going to be to find and graph the asymptotes. So you want to locate the vertical asymptotes as well as locating any horizontal asymptotes. And we walk through the process about how you can find that and how to find the asymptotes we talked about in the previous video. Then once you find the asymptotes, now we're just trying to plot some additional points to get an idea of where the graph is going to go. So always a good idea, find and plot the x and y intercepts. And then from there, you want to plot any points that lie between and beyond each x-intercept and vertical asymptote in order to determine what the overall behavior is going to be. And then we graph the function. Now keep in mind, this method will give you a good sketch of the graph of a rational function. It's not going to be an overly precise graph of a rational function. For that, you can use a graphing calculator or some other means, or you could just plot all the points. But this particular step will allow you to relatively quickly, sketch the graph of a rational function. So let's look at a couple of examples. All right, so for our first example, we're going to look at the function f of x equals x plus 5 over x squared minus x minus 2. So we begin this function by, first of all, identifying if there are any holes. So we can do that by just factoring the numerator and the denominator. Numerator, nothing to factor there. It's just going to be x plus 5. X squared minus x minus 2. If we factor that, that'll give us x minus 2 times x plus 1. All right, so we can see here there are no common factors. So this graph will have no holes. All right, so now the next step is going to be to identify the asymptotes. All right, so now remember, for the vertical asymptotes, all we need to do is just set the denominator equal to 0. So our denominator, x minus 2 times x plus 1 equals 0. So when we set these factors equal to 0, should be pretty easy to see. We'll end up with solutions of x equals 2 and x equals negative 1. So those will be our vertical asymptotes. So vertical asymptotes will be located at positive 2 and negative 1. Now, what about the horizontal asymptotes? Well, remember that for the horizontal asymptotes, we look for the degree. We compare the degree of the numerator and the degree of the denominator. Now, the degree of the numerator in this case is 1 because it's a linear expression. The degree of the denominator is 2. So we have a smaller degree in the numerator than we do in the denominator. So therefore, the horizontal asymptote will be just the x-axis, or y equals 0. Now, from this point, we want to plot we want to find the x-intercepts and the y-intercept. So if we do that here, to find the y-intercept, we're going to set the x value equal to 0. So if we plug 0 into the original function, it's going to be f of 0. So we'll have 0 plus 5 over 0 squared minus 0 minus 2. So this will give us a result of negative 5 halves. So our y-intercept will have the coordinates 0 and negative 5 halves. The x-intercept, for that we set the entire function equal to 0. So we have x plus 5 over x squared minus x minus 2 equals 0. Now, one of the nice things about rational functions is that being a fraction is equal to 0 only when the numerator is equal to 0. So all we really need to do here is just set the numerator equal to 0. X plus 5 equals 0. So x is going to be equal to negative 5. So our x-intercept will have the point negative 5 and 0. All right, so let's plot what we have so far. And I'm just rewriting the asymptotes that we have, as well as the x and y intercepts. All right, so I want us to do this. We want to go ahead and look at what we have so far, and I accidentally cleared everything out. That was smart. There we go. So I just want to take a look at what we have so far. So we're going to graph the information that we have thus far to see what additional points may be necessary. All right, so we have our vertical asymptotes at positive 2 and negative 1. All right, so I'm going to use a light color for the asymptotes. So positive 2, and negative 1. And then we have a horizontal asymptote, which is the x-axis, where y equals 0. All right, so we mark that off. And so now we have x-intercepts and the y-intercepts. So the y-intercept is located at 0, -5/2. So that's going to be -2.5. So that'll be located here. And then the x-intercept was at -5, 0. All right, so now we want to plot some additional points to figure out what the overall behavior is going to be. Now, if we take this one piece at a time, all right, we can see that there are a number of different possibilities that we could have, which is going to guide what our choices are going to be for the additional x values that we choose. All right, so now, starting from the left side, over here we have a number of different possibilities. Now, since we know what the x-intercepts are, beyond the x-intercepts, the graph is either going to be above the x-axis or below the x-axis. So from -5 off to -infinity, the graph could move to the left. It could be above the x-axis or it could be below the x-axis. Likewise, between -5 and the vertical asymptote of -1, this thing could be above the x-axis, but now if it goes above the x-axis, it must continue on and approach the vertical asymptote going upward, or it could approach the vertical asymptote going downward. So since we don't know what's going to be happening here, we'll need to choose a value that's less than -5 to find out whether it's positive or negative. So we can choose -6 for an x value, or -7 or -10, it doesn't matter. And then we'll also need to choose a value that's between -5 and -1. So here, let's say we choose -3. So that'll give us an idea of what's happening there. Now, if we plug these values into the original function, all right, so if you plug these values into the original function, and I'm going to go ahead and do that on separate paper because this is something that you guys can do on your own. All right, so for the value of -6, our y value is going to be -0.025. All right, now the main thing here is that it is going to be a negative value. So that's going to be important to us. All right, so that tells us that at least on this side, it's going to be below the x-axis. Now, if we plug in -3, for -3, we get positive 0.2. So the positive value there tells us that between -5 and -1, it'll be above the x-axis. So for this portion of the graph, or for this portion of the function, we can pretty much, it's going to be below the x-axis here, above the x-axis for -3. So it looks like the behavior of the function is going to tend upward to positive infinity. And then on the other side, it's going to tend downward. Now, since the horizontal asymptote was the x-axis, this isn't going to continue to go downward. Basically, what happens is that it crosses, goes down, and eventually it's going to basically smooth itself back and make its way back toward the x-axis. Okay, so just keep in mind that this isn't necessarily drawn to scale. And I'm going to try this one last time. There we go. All right, so now we know what's happening on the left side. Now, what about in between the vertical asymptotes? Well, note here that we have this single point on the y-axis at 0, -5/2. We know that the graph will tend towards the vertical asymptotes. It will tend toward the vertical asymptotes. So with that in mind, there are no x-intercepts in between these vertical asymptotes. So now, because of that, there's only one possible direction the graph can go. It's got to go down. If it goes up towards the asymptotes, it has to cross the x-axis, which means that there would be x-intercepts. But we found all the x-intercepts. There was only one x-intercept at -5. And so we know that's not going to happen. So the only direction that this can go from here is down. All right, so we can sketch that off there. On this side, it's possible that the graph may come up a little bit, but then it eventually has to make its way down. Now, if you want to be a little bit more precise with that, you can plot maybe see what happens at x = 1 to get a better idea of what happens there. But once again, we're just looking at trying to sketch the graph to get an idea of what the basics of the graph is going to look like. All right, so we have that there. And if you're unsure as to what the direction is going to be, you can always choose to plot more values. So that's what's going on in the middle. Now, for the right side, well, we've got two possibilities here, and there's only two. Since there are no x-intercepts, it's not going to cross the x-axis, so we could see movement. So the graph will either have to tend toward the positive, stay above the x-axis, or stay below the x-axis, and then move towards the vertical and horizontal asymptotes. So all we need to do here is just to figure out whether it's going to be positive or negative. So we'll choose x value, anything greater than 2. So we can choose, say x = 4. Plug that into the function. So if we let x = 4, we'll get a y value of 0.9, 0.9. Being a positive value, that confirms that the graph will tend upward toward the vertical asymptote at 2, and then tend toward the horizontal asymptote of the y-axis as x increases without bound. All right, so here you have a sketch of the graph of the function. I apologize that my writing isn't quite as steady, but this gives you an idea of what the graph looks like. Now, let's take a look at one more example. All right, so for this example, we have the function f of x = x³ minus x over x² plus 5x minus 6. Okay, so now from here, looks like I was having a little bit of audio trouble, so hopefully that's been rectified. So from here, once again, we follow the steps. Identify any holes in the graph. So now to do that, we have to factor this out. So now if we do the factoring up top, that's going to be x times x squared minus 1. We have a common factor, which we can further factor as x times x plus 1 times x minus 1. In the denominator, x squared plus 5x plus 6, that's going to be x plus 6 times x minus 1. So we have a common factor here of x minus 1, which cancels out. So now what does that tell us? That means that we're going to have a hole where x minus 1 is equal to 0 or at x equals positive 1. So now the equivalent expression is going to be x times x plus 1 over x plus 6. So now we look at the asymptotes. We have a hole at x equals 1. The asymptotes, the vertical asymptote will be when the denominator is equal to 0. So here we can see that we have a denominator of x plus 6. So when we set the denominator equal to 0, we'll have a vertical asymptote at x equals negative 6. For the horizontal asymptote, now this will take up some work here because when we look at the degree of the numerator, and I'm going to take the simplified version, the degree of the numerator here is going to be equal to 2, and the degree of the denominator is going to be equal to 1. So when we have a larger degree in the top than in the bottom, this means that we're going to have a slant or an oblique asymptote. So now to find that slant asymptote, we have to do long division. We'll have to divide x times x plus 1, or x squared plus x by x plus 6. All right, so if we do the division, now in this case, we can use synthetic division because we're dividing by a linear factor with the leading coefficient of 1. So we'll place negative 6 here. The numerator will have 1, 1, and 0 since we don't have a constant term here. And so doing the synthetic division, we bring down the 1. 1 times negative 6 is negative 6 plus 1 is negative 5. Negative 5 times negative 6 is 30, plus 0 is going to give us 30. All right, so the division will be x minus 5 plus 30 over x plus 6. But now remember, we're only concerned with the quotient, not the remainder. So our slant asymptote will simply be the equation y equals x minus 5. So Now that we've got the vertical asymptotes, we've got a slant asymptote. So now we're going to go ahead and find the x and y intercepts. All right, so I'm just going to write down the information here when I clear the screen. All right, so now for the x and y intercepts, remember that for for the y intercept, we'll set x equal to 0. So the y-intercept, if we find f of 0, so that's going to give us 0 cubed minus 0 over 0 squared plus 5 times 0 minus 6. And so, of course, here you've got 0 over negative 6, so that's just going to be equal to 0. So our y-intercept will just be the 0.00. So now we need to find the x-intercepts. All right, so remember what we said before, the x-intercepts will only occur when the numerator is equal to 0. So with the x-intercepts, we can set the numerator x times x plus 1 equals 0. Now, I only worry about, and I should have done this with the y-intercept, but it doesn't matter. The y-intercept or the x-intercept, we're going to look at the simplified version of the rational expression. Now, I should have done that for the y-intercept as well. But once again, it doesn't make a difference. The y-intercept turned out to be the same. So here we set each factor equal to 0. It should be pretty easy that we'll have x equals 0 and x equals negative 1 for our x-intercepts. So one of those, the x-intercept of 0, was also the y-intercept. All right, so we have those values for the x-intercepts. So now let's go ahead and plot what we have so far to see what additional points may be necessary. Now, just as a side note, we don't have to worry about the original equation, because with the original equation, there would be an additional supposed x-intercept at positive 1. But remember, that doesn't even count because that was where there was a hole in the graph. The function isn't defined for that value. All right, so we don't even look at what's happening in the original function for the intercepts. All right, so I seem to have inadvertently Okay, so now let's take a look and plot what we have so far. Okay, so I'm going to adjust the graph somewhat because things are going to fall outside the borders a little bit. All right, so we have the hole at x equal 1. Right now, we don't worry about the hole to begin with. We have a vertical asymptote at x equal -6. All right, so we'll put the light colored vertical asymptote there. And our slant asymptote was the equation y equals x minus 5. So now that's going to be a line having a slope of 1 with a y-intercept of -5. So if we graph that, okay, so the slant asymptote is going to reach like this. So now you can see that the cross between the vertical and the slant asymptote is pretty low, and that's one reason why I wanted to sort of shrink the grid down so we could see everything. All right, so now let's take a look at the x-intercepts and the y-intercepts. So the x and y-intercepts, y-intercept, which was also the x-intercept, was at 0, 0. So you have 0, 0. And then we also have the x-intercept at -1, 0. All right, so now we plot these 2 points. All right, so now we need to figure out what the overall behavior or the possible behavior of the function is going to be to see what additional points we might need. All right, so now let's start over here to the left of the vertical asymptote at -6. Now, the behavior of rational functions tells us that rational functions will tend toward the vertical and horizontal or slant asymptotes. So on this side of the graph, we have 2 possibilities. Either the graph is going to approach -6 from the left, from the positive side. In other words, it's got to go up, it's going to be coming up from here, and then it's got to approach the slant asymptote. So either it's going to behave like this, or it's going to behave underneath the slant asymptote and then go down and approach the vertical asymptote of -6 on the downside. Now, which of these possibilities do you think it might be? Well, considering the fact that we already found the x-intercepts and they're at 0 and -1, there will be no other place where the graph crosses the x-axis. In order for this possibility to exist on the upside, it's got to cross the x-axis. So since we know there are no more x-intercepts, that will not be a possibility. And so we can pretty much conclude that for this side of the graph, it's going to tend to the downside. So I'm going to redraw that, make it a little bit neater. Now, once again, you could confirm if you're not quite sure, this is something that we could confirm by plugging in any x value that's less than -6, like -7 or -8, into the original function. All right, so now let's look at the other side. Well, now on this side, we have -1 and 0 as x-intercepts. Once again, knowing that the graph is going to tend toward the vertical asymptotes, all right, between -6 and -1, there are actually 2 possibilities. It could tend up toward the vertical asymptote or tend down toward the vertical asymptote. Now, one thing I failed to mention before is that it is entirely possible for the graph to cross a horizontal or a slant asymptote. There's nothing wrong with that happening. So that is a possibility. All right. So now we'll need to figure out what's happening between -6 and -1. So we'll choose some value, say -4, and we'll plug that into the function to see what we get from that. Now, another additional point we'll need to know is we'll need to know what's happening between 0 and -1, because it may bounce above the x-axis or it might bounce below the x-axis before it comes back to 0. So we'll need something between -1 and 0. So we'll look at -1/2 for a value. And then from 0 to the right, well, with this one, I think it's going to be a foregone conclusion what's going to happen here, because there are two possibilities. It could either be positive, okay, or it's going to be negative. But now there's one small issue. We know that the rational functions, horizontal and slant asymptotes, dictate the end behavior of a function. So now if it goes down below, it has to come back up and basically approach that slant asymptote. Now, in order for that to happen, what's going to be the case? It's got to cross the x-axis again. But we found all the x-intercepts, so we know that's not going to be a possibility. So in this case, we can save ourselves a lot of time here. We don't need to graph. We know it's not going to go below the x-axis. So at least from 0, the graph is going to continue above the x-axis and approach that slant asymptote. All right, so now let's plot these two values for x into the original function and see what we get. All right, so we have x cubed minus x divided by x squared plus 5x minus 6. All right, so if we look at -4, at -4, the y value is equal to 6. And at -1/2, we get negative 0.045. So now, once again, what we're paying attention to is whether it's going to be positive or negative. So we see that at -4, we have y value of positive 6. So being positive, that tells us definitely that this graph from -1 is going to continue to go upward toward the vertical asymptote. Between -1 and 0, at -1/2, we got negative 0.045, very small but negative. So that means it's going to go below the x-axis and then make its way back up to 0 and then go up from there. All right, so now from here, what do we do? Now there's one last thing that we have to consider, because we got the sketch of the graph, but the one thing that we have to consider is the hole. Remember, we had a hole at x equal +1. So now that means that we're going to have to adjust what happens on this side to account for that hole. So what's going to happen is that we're drawing this. As this goes up, at x equal 1, we're going to have to put an empty spot there to indicate that we had a hole in the graph. Okay, so the hole in the graph is going to look something like that. Usually you have like an open circle to represent the location of the hole in the graph. All right, so that would be the sketch of this this rational function. So now, definitely, it was a little bit more work for us to do this particular one because we had the hole in the graph and we had the slant asymptote. But the process, as you can see, did not change. We identified the hole, we identified the asymptotes, the vertical and the slant asymptote, we found the intercepts, and then we plotted some additional points to determine what the behavior is going to be. Now, one thing that can save you some time, as we did in these examples, I used some deductive reasoning to determine what the behavior of the function was going to be for certain regions. Now, you can use that deductive reasoning as well, but if at any point you're not quite sure where it's going to go, just plot additional points. It doesn't take too long to do that. And obviously, if you want a correct graph or a correct sketch of the graph, it's better to be safe than sorry. Okay, so I hope that this was helpful. Um, if you have any questions, obviously we can talk during our normal class period, but hopefully this will give you an idea of how to approach graphing the rational functions and the things to look out for. All right, so I'll see you again soon.